civilpe.net.
All right, today we're going to further expand upon your skills as a reinforced concrete beam designer. We're going to look at the same rectangular beam we looked at previously, and we're going to explore more of the minimum steel requirements of ACI. As you can see, we've got the same beam, 12 inches wide by 24 inches deep. The only difference now is instead of 3 number 6 bottom bars, we're showing 3 number 4 bottom bars. We've got the same 2 number 4 top bars and the number 4 stirrups at 12 inches on center. We're using the same strength we used before, 6,000 psi. The yield stress in the steel is 60 ksi. So what we want to do is we want to determine if this section can carry a factored moment, M sub u, of 40 kip feet while still satisfying all ACI requirements. Our assumptions are going to be exactly the same as they were before. Plane sections remain plane. The maximum concrete strain at the extreme compression fiber at failure is assumed to be 0.003. The tensile strength of concrete is neglected. And once again, to simplify our calculations, we're going to neglect the compression steel in this calculation. So those 2 number 4 top bars, we're going to pretend like they're not there. So let's start by constructing our stress and strain diagrams once again. For our strain diagram, we're going to assume that at failure, the strain in the concrete is 0.003. And because plane section remain plane, we can assume that the relationship between the extreme tensile fiber, or the extreme tensile steel, and the extreme compression fiber is linear. C is our depth from the extreme compression fiber to the neutral axis, and D is the depth from our extreme compression fiber to the centroid of the steel. From there, we can construct our stress diagram. Here we've got the compression force is a distributed force over a depth A, which is the depth of our Whitney stress block. The resultant of that is this C right here, this compression force. Down here we've got the tensile force, which is equal to the area of the steel times the stress in that steel, or T. And D is the depth from the extreme compression fiber, once again, to the centroid of that steel. I added one more section just to clarify this a little bit more. You see in this section of the beam, you've got the shaded area represents the compression zone. So this stress diagram is a cross-section of this section right here. So the compression zone is depth A from that extreme compression fiber up here, and it acts over the entire width of that beam. So let's start by calculating D, the depth from the extreme compression fiber to the centroid of our steel. So D is equal to the height of our beam minus the clear spacing minus the diameter of the stirrup minus the diameter reinforcement divided by 2. You substitute those properties in and you calculate it out, you get the D for this section is 21.75 inches. So now let's use that to solve for A, the depth of our Whitney stress block. From the rules of equilibrium, we know that the compression force C must equal the tensile force T, and equal and opposite, or else this beam would be sliding off into space. So that compression force per ACI is equal to 0.85 times F prime C times B times A. That's that Whitney stress block that I've referred to several times now that ACI uses as an approximation for the stress in concrete. B is the width of the compression zone, A is the depth of that stress block. Substitute our values in, we get that the compression force is equal to 0.85 times 6,000 psi times 12 inches times A, the depth of that stress block, which equals 61,200 pounds per inch times A. Now we need to calculate the tensile force T. We know that T is equal to the stress in the steel times the area of the steel. Here we're going to make that same assumption that the stress in the steel yields. We're assuming that the strain in that steel is beyond which the strain in that steel is beyond the yield strain. And in so doing, we know that the stress in the steel is equal to the yield stress of that steel, or 60 ksi. A sub S is once again the area of the tensile steel. So substitute our values in, and we get the tension force is equal to 60,000 psi times 3 times 0.2 inches squared. We've got 3 number 4 bars, and we get that tension force is equal to 36,000 pounds. So now we've got the variables that we need in order to solve for A, the depth of that stress block. So now we know that A is we get our equation, set C equal to T, and we get 61,200 pounds per inches times A is equal to 36,000 pounds. So solving for A, we get that A, the depth of that stress block, is equal to 0.588 inches. So now using this, we can solve for C, the depth to our neutral axis, and determine the strain in that steel. From ACI, we're given that A is equal to beta 1 times C, and beta 1 is a factor that relates the depth of the stress block to the neutral axis based on the concrete strength. Now for 6,000 psi, we can calculate this out and get that our C is equal to 0.784 inches. So now with C, we can calculate the strain in that extreme tensile fiber. Using similar triangles, we can figure out that C divided by the strain in the concrete is equal to depth D divided by the strain in the concrete plus the strain in the steel. Rearranging and putting in our values, we get that the strain in the steel is equal to 0.08. So what does this tell us? From ACI, we're given that a section is considered tension controlled if the strain in the extreme layer of tensile steel is greater than 0.005. The strain that we've calculated is 0.08, which is much greater than that 0.005. Therefore, we can consider this tension controlled. That means that we get a phi factor of 0.9 for our section. Once again, I just want to walk you through this. We need to determine the strain at which the steel yields and check our assumption that the steel in fact yielded. We know that Young's modulus is equal to the stress in the steel divided by the strain in the steel. So if we want to find the yield stress, or the yield strain, we set Young's modulus equal to the yield stress divided by the yield strain and solve for that yield strain. So substituting in, we get that the yield strain is equal to the yield stress, 60 ksi, divided by Young's modulus for steel, 29,000 ksi, and get that that's equal to 0.00207. The strain in our steel is 0.08, which is much greater than this 0.00207. Therefore, our assumption is correct, and our steel yields prior to failure. Now, you'll be dealing with 60 ksi steel quite a bit, so it's a good idea to commit this number to memory so you don't have to do this calculation every single time. 0.00207. You can see up here that we already calculated that strain in our steel at 0.08. We know that this steel yields at a strain of 0.002. So our 0.08 is greater than this 0.005, which is greater than that 0.002, so we know automatically that our strain yields, and we don't need to go through this, but I go through this for illustrated purposes. So now let's determine if the section satisfies the minimum steel requirements of ACI. This is where this example is going to differ from the previous example. So per ACI section 10.5.1, the minimum steel is 3 times the square root of f prime c over f sub y times the width of the web times the depth, which has to be greater than or equal to 200 over f of y times the width of the web times the depth. So for us, our minimum area of steel that we calculated comes out to 1.01 inches squared. We only have 0.6 inches squared in our section, which is much less than that 1.01 inches squared. Therefore, we don't satisfy this minimum steel requirements per ACI. But all is not lost yet. ACI section 10.5.3 gives you kind of a loophole in this. It says the above mentioned provision does not need to be satisfied if at every section the area of steel provided is at least 1/3 greater than that required by analysis. So what we need to do is we need to calculate the required amount of steel for our section to carry a 40 kip-foot moment and determine if that amount of steel provided is at least 1/3 greater. The amount of steel that we provide is at least 1/3 greater than that for the calculation. So let's calculate the area of steel required to carry a moment of 40 kip feet. Using force equilibrium, we need to find a relationship between A sub s, the area of steel, and A, the depth of that Whitney stress block. So we know that the compression force must equal the tension force. So 0.85 times F prime C times the width of the beam times A, the depth of that stress block, must equal A sub S, the area of steel, times F sub Y, the yield strain, or the yield stress. Substitute all of that in, and we get a relationship between the depth of the stress block and the area of steel. A is equal to 0.9 per inch, or 0.98 per inch times area of steel. So using that, we need to calculate the moment of our section, the moment capacity of our section, by taking the moments about the compression force C, and determine our moment capacity phi times m sub n, and set that equal to the factored moment m sub u. So we know that phi mn is equal to phi times the tension force. We're once again taking our moments about this center of this compression force. So phi mn is equal to phi times the tension force T times the overall depth minus A over 2. So that moment arm right there. So now let's set phi mn equal to mu. Set that equal to the phi mn that we just calculated. So we get 40 kip feet. And then I put this in here times 12 kip inches per kip foot to convert it from kip feet to kip inches to make sure all our units correlate correctly. Set that equal to 0.9 times A sub s times 60 ksi times 21.75 inches, which is our D, minus A over 2. Now we could substitute in that equation that we had before of A equals 0.98 per inch times area of steel into that above equation and rearrange it a bit. And what we get is 26.26 kips per inches cubed times the area of steel squared minus 1,174.5 kips per inch times the area of steel plus 480 kip inches is equal to 0. So what does that look like? That looks like a quadratic formula. So now we need to solve this. We need to go back to our old friend, the quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac over 2a. I know a lot of you have this committed to memory because we use this quite a bit. So for our equation, we substitute a, b, and c into that quadratic equation, and we come out with this. Our area of steel is equal to negative 1,174.5 minus the square root of negative 1,174.5 squared minus 4 times 26.46 times 480 divided by 2 times 26.46. And that's all from that previous equation that I showed you. So calculating this out, we get an area of steel required for this section of 0.41 inches squared. So now we need to determine if we satisfy that minimum steel requirement per ACI 318 section 10.5.3. We know that, or we need to figure out what 1 1/3 times the area of steel required is. So 1.333 times that area of steel required, 0.41 inches squared, is equal to 0.55 inches squared. So as long as we provide a section with steel greater than 0.55 inches squared, it doesn't matter if we don't meet that first minimum steel requirement. We have 0.6 inches squared, which is greater than that 0.55, so therefore we satisfy all sections of ACI, all the requirements of ACI for an applied factored moment of 40 kip feet on this section. If you have any questions or comments, please send me an email at info@civilpe.net and check us out on the web at http://www.civilpe.net for more videos and more help.